का वॉल्यूम अपन को पता है। लगता है क्या हमें पता है।
You can clearly see from this equation, isn't it? So if the zeta is equal to 1, in that case this becomes 0, isn't it? So minus zeta by tau, and this also becomes minus zeta by tau. So you can see that T1 and T2 both are same, isn't it? So in that case tau1 becomes tau2. Tau1 becomes tau2. So whenever we have tau1 and tau2 both are same, in that case we get a critically damped system, and this particular expression is not valid when tau1 is equal to tau2. So you can see that this particular expression is doing what? This particular expression is actually converting this generalized expression in the form of two capacities, where the first capacity will have a time constant of tau1 and the second capacity will have a time constant of tau2. That is what we have done here. Okay. If you closely look at this expression, this is what the conclusion you are going to gain. Okay. Of course, if you look at it closely, isn't it? I don't know how many of you are looking at it closely. That is the question. Okay. So we said that when zeta is greater than 1, then we get a overdamped system. Overdamped system is what? The system which is having the exponential response like this. Then we have a critically damped system which is also have an exponential response, but it will be slightly faster compared to overdamped system. And if you look at the underdamped system will be again faster than the overdamped and critically damped system, but it will associated with oscillation. And these oscillations are going to die out. And when you look at the undamped system is a system where zeta is equal to 0, and in that case you will get a response like this. There is a sustained sign there, which is not going to die out, isn't it? So you get an undamped system where your roots are located on the imaginary axis, otherwise you will not get undamped. Okay, so these are small inferences which are extremely useful when you are analyzing the system response. Okay. Okay. So in this, okay. physically you are asking or mathematically you are asking? Physically you are asking, you will get this. That one. Okay. So when we will look at two tank system, then we will look at this particular case what our friend was asking. When we will have tau 1 is equal to tau 2. Actually your answer is when the size of the tank is same as the size of the other tank, then tau 1 is same as tau 2. Okay, you will get a critical answer. We will come back to this derivation when we will look at the tank system as we go ahead. Okay. So now as I said, this particular expression is generalized expression and this expression is valid for both overdamp system as well as underdamp system. This expression is not valid for critically damped. But for overdamp and underdamp, you can use the same expression and find out the answer. Okay. So this is what we have seen in the last class. We said let's look at the system, overdamp system when zeta is greater than 1. In that case again we are looking at the step input of magnitude unity. If you put that, then we get f of s equals to 1 by s. This is the expression, so ys comes out to be kp divided by s in kp divided by s into tau square s square plus 2 zeta tau s plus 1, isn't it? Now remember this is the same expression which we had earlier. This is the same expression. Right. That means we are bound to get the same solution. The same solution we are going to get. Correct. Now in this particular solution, put tau 1 equals to tau divided by zeta minus under root zeta square minus 1. I can put that easily, there is no problem. Why? Because zeta is that we can do it easily. Just by, so see in this particular equation, since zeta is greater than 1, I can write down tau 1 like this easily. If I put tau 1 equals to this in this particular expression, ultimately what I am going to get is this. This is what you are going to get. Okay. Correct. So the expression what we are expected to get for a overdamp system is yt is given as kp in the bracket 1 minus e raised to the power minus zeta d by tau cos hyperbolic under root 1 minus cos hyperbolic under root zeta square minus 1 t by tau plus zeta by under root zeta square minus 1 sin hyperbolic under root zeta square minus 1 t by tau. So you can see that we have rearranged the equation in such a way that the term in this under root is going to be positive, isn't it? Because zeta is greater than 1, and that is why we have arranged this equation in terms of hyperbolic cos and hyperbolic sin. Okay. Alright. How the response will look like for a overdamp system? For a overdamp system, as you can see that this green line is a first order. Green line is a first order response. Green line is a first order response, you can see. Whereas if you look at the other three cases are for the second order system. So second order system, this particular line with zeta equals to 1, so that is critically damped. As the value of zeta increases beyond 1, you will see that the response becomes more and more delayed. The response is becoming more and more delayed as the value of zeta increases. So if you compare first order response and the second order response, what you can conclude here is second order system is going to give you a sigmoidal response. Second or a higher order system is going to give you a sigmoidal response, which is delayed in the starting, isn't it? Which is you can see here it is delayed compared to this. Alright? And as the value of zeta increases, your system response is going to become more and more sluggish as the value of zeta increases. Okay? Is it clear? But if you look at t tends to infinity, if you take t tends to infinity, then you are going to get the same steady state value. Same steady state value equals to Kp is what we are going to get. I can derive that easily from this expression. I can find out yt at t tends to infinity from this expression directly. Isn't it? I can apply a final value theorem here. So I can find out yt at t tends to infinity is equal to what? Limit s tends to 0, s into f of s, s into y of s. Isn't it? So if you find out that, you will directly get only Kp. Only Kp you are going to get. Okay? So ultimate value is same when t tends to infinity for all these cases. So from this again we can find out the physical significance of Kp in this case. So physical significance of Kp in this case is nothing but change in the output divided by change in the input. Correct? And this physical significance is exactly same as first order process. There is no change. Remember I said the time constant of the second order process is not same. Second order process, the time constant which we are looking at. First order system time constant is nothing but what? Time constant is nothing but capacitance into resistance, and it is related to the speed of this source. That is the physical significance of time constant in the first order process. But if you look at the time constant in the second order process, it is not related to the speed of response. In the second order system, the time constant is nothing but the natural period of oscillation. That is what we are going to derive as we go ahead. Okay. So time constant for the second order process is nothing but natural period of oscillation. Okay. Alright. So this is for a second order underdamped, overdamped. Let's look at second order critically damped. So critically damped, this is the same expression we are having, isn't it? We are assuming that the zeta is equal to 1. So zeta, if we put this zeta value equal to 1, then what we are going to get? This becomes a very well organized quadratic equation with a root equals to 1 by tau. Isn't it? So I can represent this particular expression as s plus 1 by tau square, and tau I can take in the numerator. So s by Kp by tau square, and here in the denominator we will have s into s plus 1 by tau square. So you can see that this particular root is a multiple root. There are two roots located exactly at minus 1 by tau. Isn't it? So whenever we have a multiple roots, what we get? What we get whenever we have multiple roots? Whenever we have multiple roots, we get such terms 1 plus t by tau. Is it clear to everyone? So now this particular expression, okay, this is similar. I don't know whether you are able to correlate from where we have written this. We had one example solved earlier. So this is the example we have solved. Remember here we are having multiple roots. So whenever we had a multiple roots, we get a partial fraction slightly in a different way. And if you invert that into a time domain, you get a time term. Remember here 1 is there, here t is there, here t square by 2 is there. Isn't it? So if you take this e raised to the power minus t common, actually you get c1 plus c2t plus c3 t square by 2. So this common bracket, what we are getting here, exactly similar. See, in this case also we are getting 1 minus t plus 1 by 2 t square. So this type of common term in terms of t you are going to get, isn't it? So that is what we are getting in this case also. And we are writing that directly. So here you can see the same term we have obtained. 1 minus 1 plus t by tau. Isn't it? If I would have had one more root in that case, I would have had one more t term here, t square by 2 factorial. So remember that term goes with the factorial. Okay. So you can see that this additional term is coming because of multiple root, isn't it? This additional term is coming because of multiple. So this is the expression we have obtained. So very simple expression we are getting in case of critically damped. Unlike the overdamped, in the overdamped case we got slightly complicated equation. This is slightly complicated equation. But in case of critically damped, we are getting a very simple exponential type of response. There is no confusion here, isn't it? Correct. Let's look at the third case. So in the third case, underdamped system. So underdamped system is a system where the damping factor zeta is less than 1. Less than 1. Again, we can derive the expression for underdamped system by using the same generalized expression. That generalized expression given was this. Remember, this is the generalized expression. Kp into 1 plus tau 1 e raised to the power minus t by tau 1 minus tau 2 e raised to the power minus t by tau 2 divided by tau 2 minus tau 1. Okay. So this is the generalized expression we are having. We can use the same generalized expression and we can derive the expression for underdamped system. The only difference in that case will be, remember in this case the zeta is less than 1. Zeta is less than 1 in case of underdamped system. So you will be getting a iota term here, isn't it? And because of that you are getting a cos and sine term instead of cos hyperbolic and sine hyperbolic, isn't it? Correct? So you can see the expression changes slightly here. So this is the generalized expression. With that, the expression comes out to be yt is equal to kp 1 minus e raised to the power zeta t by tau cos under root 1 minus zeta square we have taken, that minus sign we have taken out, isn't it? Plus zeta divided by under root 1 minus zeta square fine 1 minus zeta square divided. Correct?
जेवायला
छोटी हो मैं तो एक बार वहाँ फोन में आ जा रहा हूँ कि भाई हम फोन करेंगे पिताजी 19 रुपए एहसान रखवाना तो मैंने मैं कह रहा हूँ बोरा डेली ले जानी काटे रोटी एहसान को एहसान रखवाओ अरे 20 लाख मानने पड़ जाएगा यार, क्योंकि बाकी साइड में अपनी साइड पे गंद हो रहा है, अपने दूसरी साइड पे गंदा रहता है।
अंदर का स्पेस n pi by omega again for the first peak n will be equal to 1 because at 0 it is a value. So at first peak n is equal to 1, so that will give you t will be given as pi by omega. Now this t equal to pi by omega you can put it in this equation. This is the expression we started with. Remember? If I go back, this is the expression we have started with, isn't it? So here t, this t I can replace by pi by omega. If I replace by pi by omega, that omega will get cancelled out. So you will have sin pi, and here what you are going to get? Cos pi, isn't it? That's what you are getting. 1 minus under root 1 1 upon under root 1 minus zeta square that we have taken common. Exponential of remember here we are having zeta t by tau. So this t again we have replaced by n pi by omega. So that will become what? N pi by omega. So pi by omega if I put here, so zeta pi by omega tau. So that is what we have written here. And this omega again replaced by this expression. Omega is replaced by 1 minus zeta square by tau. So ultimately what you get here is 1 minus 1 upon under root 1 minus zeta square exponential of minus pi zeta divided by under root 1 minus zeta. That is what you are going to get by replacing omega and the other terms here. And this term is zeta into sin pi plus 1 under root 1 minus zeta square cos pi. Cos pi is minus 1. This is 0, isn't it? This minus sign is multiplied with this minus sign that becomes plus, isn't it? So what we get is 1 plus exponential of this entire term, isn't it? This 1 minus zeta square will get cancelled out with this 1 minus zeta square. So ultimately what we are left with is 1 plus exponential of minus zeta pi divided by under root 1 minus zeta. That's it. This is what you are left with. And this particular term yt by kp at n equals to 1. So this is nothing but what? We are finding out this value at the peak here. This is the value we have found out, which is nothing but what? This is nothing but what? A plus b. Isn't it? But b is 1. So you can find out what is a. So a comes out to be yt by kp minus 1, so that comes out to be exponential of minus zeta pi divided by under root 1 minus zeta square. This is the same expression we have derived here, which is written here. This is the same expression. Okay. A similar expression you will get for the third peak also. So for third peak you will get 3 zeta pi here. Instead of zeta pi you will get 3 zeta pi. And if you divide this 3 zeta pi divided by this original term here, what you are going to get? You are going to get 2 zeta pi divided by under root 1 minus zeta. So that is what we have derived as a decay ratio square. Sorry, overshoot square. That is what we are getting as a decay ratio here. So see, when you are putting n equals to b, the expression what you are expected to get is minus 3 zeta pi divided by under root 1 minus zeta square. So that is nothing but c. And c divided by this a is nothing but decay ratio. So if you divide this term by this term, what you are going to get is exponential of minus 2 zeta pi divided by under root 1 minus zeta square. And that is nothing but overshoot square. Correct? Now similarly for rise time. Rise time is what? Rise time is the time at which you are first switching to the value equals to 1, isn't it? So in this case, yt by kp is given by this expression, isn't it? This expression is what we have obtained, and this is equal to just 1 at the rise time. So that means what? This 1 will get cancelled out with this 1, and this entire term will get cancelled out. So ultimately sin omega t plus 5 should be equal to 0 for us. Again, if you rearrange, the sin omega t plus 5 will be 0 only and only if when omega t plus 5 is equal to n pi. Isn't it? So from this we can obtain this t, which is nothing but the rise time, which comes out to be n pi minus 5 divided by omega. Now which value of n we should use here? Which value of n we should use? Value of n should be in this case 1, not 0. Because 0 will give you what? 0 will give you a negative value of rise time, which is not practical in this case. So we have to use n equals to 1 in this expression. Okay. So if you use n equals to 1 in this particular expression, you are going to get the rise time. Slightly more complicated derivation. Please go through this derivation. Is not there in your book. In your book, these are given directly. These are not derived in your book. Okay, so please go through this derivation carefully. Alright? It's not there in your book. It is not there in any of your books. So please see the derivation carefully and go through. There are a lot of interesting concepts hidden in this derivation. Okay. Almost I think I might have made almost 10 questions out of this so far. There are so many concepts are there. So those concepts will be clear to you only and only if you derive this yourself. If you think that this derivation, instead of deriving it, you will be able to use it directly, whatever is given in your printout. I think you will not be able to do that. So please try to derive it. There are small hidden concepts are there, isn't it? And of course, whatever is there in your notes or whatever is there in the book, that is not going to come. Things will come beyond this, isn't it? Correct? So that only you will be able to do if you go through all these. Otherwise, you will not be able to do it. Okay. So we will stop here unless you have any questions, slightly mathematical though. We will see this derivation again in the next class, so that everybody is able to understand clearly. Okay? I will give you another 100 slides today. So almost 300 slides is what we will be using in this course. More than 300. They will be in printed form. You will get only in a printed. Soft copy you will not get.
अभी डालेंगे स्कूप्स में आई गेस होना चाहिए
सब कुछ ओपन है ठीक है जितना कर सकते हो करना कौन सही है चलो ओके so we will look at this derivation again in the next class. I think many people were sleeping today, so that is why we will look it again. अटेंडेंस हो गई अटेंडेंस हमारा टाइम मैच कर रहा है मेरे देखो भाई ये बराबर है कि नहीं do not mark proxy for your friend इस बार आप लोग कर चुके हैं और उसकी सजा भी हो चुकी है दोबारा सजा नहीं होगी
अभी तेरी मार्क करूँगा ना एक दिन
मार्क्स ट्रांसफर में करते
हाँ
मार्क्स ट्रांसफर
क्यों
मैं नहीं जा
मैं प्रॉक्सी लगाना बंद कर रहा हूँ
मैं भी नहीं लगा मैं तो नहीं लगा एटलीस्ट बायोटेक में नहीं लगा
HCL में लगा देता मैं
HCL की भी अभी बंद कर दी यार वो फालतू में पकड़े भाई जब इतना चल
अरे बना दे यार मुझे बना दे
अबे नहीं आता थोड़ा गैस को देखा मेरा मार्क करेगा मेरा मार्क ठीक है